Hello, everyone. I'm Xiaofeng Gao. I'm from UCLA. Today, I'd like to present our work, which is done during my internship at Honda Research Institute, USA. So in this work, we're trying to study the effects of AR-based assisting interface on drivers' situational awareness in autonomous vehicles. As we all know, fully automated vehicles are not yet developed. Thus, it is still necessary to maintain driver situational awareness. It's not only prepares the drivers for sudden maneuvers and possible takeovers, and also help drivers to form bases of trust on the automated vehicles. However, as drivers are becoming out of the loop due to the autonomous driving systems, their situational awareness will actually reduce, according to a bunch of studies. One possible solution to this issue is to use user interface based on head-up displays to provide situational information to the drivers. One example could be like highlighting detected objects using bounding boxes or semantic segmentations. Although there are quite some studies in this area, there are some limitations. One limitation is that in the current study, the scenarios are specifically designed. Also, like all objects in the current study are always highlighted or never highlighted throughout the drive. Thus, like these studies aim for studying the long-term effects of highlighting on driver situational awareness. In our work, we propose standardized scenarios of the ego vehicle near the intersections. And we also propose novel protocol to examine the short-term effects on SA of the highlighting. Here are some like basics of our user study. So our study is implemented in a Unreal Engine 4-based driving simulator. In this study, we highlight objects using the bounding boxes, and we use Kobe glasses to collect drivers' gaze data. For the situational awareness, we use the situational awareness global assessment technique, in short, SAGAT, to get the situational awareness response from the participants. And we're interested in studying the effects of highlighting on the object-wise SA in different conditions, including different traffic density, different object positions near the intersections, and different object types, including the cars and the pedestrians. First, I like to talk about how we discretize the object position in the intersection. We discretize their position based on visual saliency. As you can see in this intersection, based on the saliency, we can discretize the positions into 4 areas: the top center area, the bottom center area, the bottom left and the bottom right area, and also the top left and the top right area. For the pedestrian movements, we can also discretize based on the area discretization. For example, for pedestrian A moving across the intersection, their movement is mainly in area 1. And for pedestrian B, for example, their movement is mainly in area 4 and area 3. For vehicle movements, we can apply the similar discretizations. Now, I'd like to talk about our study design. So basically, our study have 4 routes, including 2 light traffic routes and 2 dense traffic routes. And in the light traffic routes, in the intersections, there are only 5 objects. And for the dense traffic routes, each intersection has 10 objects. In addition, each drive contains 3 pairs of intersections. For example, in light traffic routes, there are 2 forward intersections, A1 and A2, and 2 left intersections, B1 and B2, and the 2 right intersections, C1 and C2. The events happening in one pair of intersections are similar. However, the SAGAT timing is different. In A1, B1, and C1 intersections, the SAGAT question is asked at the early timing. However, in the A2, B2, and C2, the SAGAT questions are asked at a later timing. Our goal of such a design is to quantify the effects of highlighting during this delayed period. As you can see, in the picture, in A1 intersections, the object is always not highlighted. And in the A2 intersections, in the light traffic route 2, the objects in the A2 intersections are highlighted, while in the light traffic route 1, the objects are not highlighted. So basically, the A1 intersection serves as a baseline to evaluate the user's situational awareness on the objects at the beginning. And the A2 intersections help us to understand the change of the driver's situational awareness as a result of highlighting. So now I'd like to introduce our scenarios. First, for the forward scenarios, A1 and A2, the Eagle vehicle is going straight, and it is waiting by the stop sign. The target objects we're interested in to study the situational awareness is pedestrian A, car G, and the car F. The Sagat question is asked when the pedestrian A is at area 1, pedestrian G, the vehicle G is at area 1, and the pedestrian F is at area 2. Here are some demonstration videos. We first show a video showing that showing the A1 intersections where the top center pedestrian and center cars are not highlighted. And the second question is asked at the early timing. Pay attention to the top center pedestrian and the cars in the center. As you can see, they're not highlighted. And now we show a demonstration showing a late Sagat question. And also the top center pedestrian and center cars are highlighted. Pay attention to the cars in the center and also the pedestrian in the center. For the left scenarios, B1 and B2, the Eagle vehicle is going left, and it is waiting by the stop sign. The target objects we're interested in are pedestrian B, pedestrian C, and the car G. And second question are asked when the pedestrian B is at area 4, and the pedestrian C is at area 2, and the vehicle G is at area 4. So we now show some demonstration videos for this scenario. So for the B1 scenarios, it is like an early Sagat question, and the top left pedestrian, bottom center pedestrian, and top right car are not highlighted. Pay attention to the top left pedestrian, the bottom center car pedestrian, and the top right car. And in the B1 scenario, it is late Sagat question, and the top left pedestrian, bottom center pedestrian, and top right car are highlighted. Pay attention to the top left pedestrian, bottom center pedestrian, and the top right car. Finally, for the right scenario, C1 and C2, the Eagle vehicle is going right. And the target objects are pedestrian B and the car F. And the Sagat question is asked when pedestrian D is at area 3, and the pedestrian and the vehicle F is at area 3. And for this scenario, for the C1 scenario, it is early Sagat question, and the bottom right pedestrian and the bottom left car is not highlighted. So this is the bottom right pedestrian, and here is the bottom left car. And for the C2 scenario, it is a late Sagat question, and pay attention to the bottom right pedestrian, which is highlighted, and also the bottom left car is also highlighted. So for the data collection, basically we recruit 20 participants, and each participant experiences 2 drives with different traffic density. And we then collect the Sagat response using the Sagat questions, and participants is going to answer the Sagat question verbally, and they are also going to give a confidence level for each of their answers. And the confidence threshold we use is 50. So basically, from 0 to 49, we treat the answers as low essay. And for answers including like 50 to 100, their answers is treated as high situational awareness. And for the fixation, we use the Tobii glasses to collect the participants' eye movements. And we also annotate the target object locations using Vatic from this camera mounted on the Tobii glasses. And the criteria we use for the fixations is that as long as the participant's fixation is like within the 4.1 degrees with towards the center of the target, towards the center of the objects for a duration of longer than 120 milliseconds. We count that as a fixation. So here are some results of the fixation time. So as we can see from like this subfigure, the top center pedestrians get significantly more fixation when it is highlighted during the light traffic. And here are also some results with respect to the SA transition matrix across the objects. So for the transition matrix, it measures the change of situational awareness as a result of highlighting. So the darker colors in the matrix represents more proportion. As we can see, with highlighting, more users improve their SA at the light traffic, indicated by the darker color in this area compared to this area. And we also find that more drivers keep the correct answers, keep the high SA before and after the highlighting. This is indicated by the darker colors of this area compared to this area, and also darker colors in this area compared to this area. And we also find that less drivers stick to the low SA at light traffic. This is like indicated by the lighter colors in this area compared to this area. And finally, we also find that less drivers switch to the low SA, which is indicated by the lighter color in this area compared to this area, and also this area compared to this area. Finally, we are interested in the SA transition matrix for each object. And we find that for the top center pedestrian, which is the pedestrian in the A1 and AB scenario, A2 scenarios, the pedestrian A in A1 and A2 scenarios, we find significant that highlighting significantly improve the drivers' SA transitions from these two transition matrices. This is indicated by the darker colors in this area compared to this area, which shows that more drivers are able to have a higher SA, switching from a lower SA to a higher SA. And also the darker colors in this area compared to this area indicated that more drivers are able to maintain their high SA with this object. Alternatively, we also find that some objects for the bottom center car, the SA actually deteriorated after we highlight it. So for the bottom center car, it is the car F in the A1 and the A2 scenarios. So this is indicated by comparing the colors in this area and this area, and also this area and this area. Finally, we are interested in seeing the response accuracy on SA. This is measured in terms of the accuracy of the driver's target response on the target object, only in the delayed intersection. The results are similar. So for the at light traffic, the SA is able to improve significantly with highlighting for the top center pedestrian and for the top right vehicle. And at high traffic, some objects SA actually decreases with highlighting. This is for the bottom center car and the top center car. So the takeaway is that highlighting via the head-up displays actually has mixed effects on driver's SA. So it tends to have a positive impact on object SA when the traffic is light. And also when the object is originally of low visual saliency. On the other hand, the highlighting can actually negatively impact the object SA when the traffic is dense and the object is originally very salient, even without the highlighting. This, I think this can actually be explained by this figure, showing that the more information we show to the user on the user interface, the more workloads they will have, indicated by this straight orange line. On the other hand, for the situational awareness, it gets plateaued in the middle because of the high workload and decrease when the workload is extremely high. So for the future work, I think it is meaningful to develop an adaptive user interface that can highlight important objects selectively to maintain the low workload and high SA.